Good morning. We are the team MaD Condors from Universidad de Los Andes, and today we're going to present our work on the 12th AIMMS-MOPTA competition. Let's begin with the motivation of the problem that we aim to solve. Imagine we own a delivery company in which our job is to deliver packages in the following network, where each node is a potential client. Every day, there's a demand at each location that needs to be served. We are currently redesigning our operating system in order to satisfy our client's demand at minimum cost. The first and most important decision we need to make is where to open a certain amount of depots, from where the packages will be sent to the demand locations each day. Additionally, the number of vehicles assigned to each depot needs to be decided. These vehicles remain in place for the entire duration of the problem, even if they have to remain idle on certain days. With these depot locations and their fleet size fixed, we should route the vehicles, minimizing the transportation costs each day. This routing needs to be done satisfying certain constraints. First, vehicles can only depart the depot after 6 a.m. and must return to this same depot before 5 p.m. However, clients can only be served between 8 a.m. and 4 p.m. Finally, a vehicle can return to the depot at any moment to reload. This action of returning to the depot in the middle of the route will be called replenishment. So to sum up, the goal is to solve an optimal vehicle routing problem, where in addition the location of depots and the fleet size should be optimized. We need to consider that at each location there's a different cost of locating a depot. There is a cost associated with locating and maintaining a vehicle, and that we have variable costs of routing the vehicles to serve the demand. In this sense, our objective is to minimize the total daily operation costs. In the task of finding such a solution, we found three main challenges. The first one is that we needed to solve a big instance of an NP-hard problem. This was a challenge because we not only wanted to provide a great solution, we wanted to do so in a reasonable time. Our real network has about 1,500 locations all over Pennsylvania, where possible clients will be and where depots can be located. And about 2,800 connections, or arcs, to travel along between these locations. This means that we can explore billions of combinations of delivery routes and possible depot and fleet size configurations, which, even for a computer, takes a lot of time. The second challenge we found is that we needed to consider different timelines for the decision making. We have the strategic decisions that are made prior any revelation of uncertain events, such as demand, and once taken cannot be changed. And we have reactive decisions that are taken after the strategic decisions and with full knowledge of the realized demand scenario. This takes us to our third and final challenge. We need to plan strategic decisions for an uncertain demand. This makes the daily routing costs a random variable, and therefore we must consider its expected value in the optimization process. With this in mind, our solution approach is laid out as follows. In order to capture the behavior of the demand, a scenario generation phase is introduced to our methodology. This phase is in charge of using the statistical properties of past realizations to carefully select scenarios that will represent our expectation for the demand. At the core of our methodology lies the fact that a distinction is made between the strategic or first stage decisions and the reactive or second stage decisions. Of course, these two need to be connected. The first stage queries possible depot and fleet size configurations with the second stage. The second stage then evaluates each queried solution in each of the selected demand scenarios and provides feedback of its routing costs. These two stages will be solved iteratively until a suffering criterion is met. So, the connection between this scenario generation phase with the optimization process is done on one hand by passing the actual demand scenarios to the second stage subproblems, and on the other, the weight assigned to each scenario to the first stage. This weight represents the probability of occurrence of each of the selected scenarios. Intuitively, this is how our methodology works. Now, let's discuss what's behind each of the main components and how they accomplish their goals. Let's begin with the first stage. The first stage decisions will be taken by a facility location and allocation model, in which in addition the routing cost of each scenario is taken into account. This model aims to minimize the total operation cost by minimizing the depot location and vehicle allocation costs, but as well an estimate on the routing cost given a depot vehicle configuration. Originally, the number of depots to open was considered to be a constraint of this model, but our solution scheme can successfully suggest the number of depots to open by dropping this constraint from the model. The estimation of the second stage cost will be made by a cutting plane approach, in which the feedback of the second stage will be essential. We will come back later to this approximation of the routing cost, since it is one of our main contributions. In the second stage, a multi-depot vehicle routing problem needs to be solved for each scenario. Therefore, the solution scheme for the second stage is a little bit more complicated. For this task, we use a column generation approach, in which the set covering master problem selects feasible routes generated by subproblems to satisfy each scenario's demand. In this solution scheme for the multi-depot VRP, the route generators play a crucial role, since all the complexity of the feasible routes rely on the model that finds them. The problem of finding a route is reformulated as an elementary shortest path problem with resource constraints and replenishment. In order to do so, a reformulation to the network is done by representing the depot with different nodes: one start node, one end node, and several replenishment nodes. Then, a feasible route is obtained by finding a minimum cost elementary path from the start node to the end node, meeting all the time windows and capacity constraints. The base algorithm used to find such paths is an algorithm that has been developed and improved by our research group, COPA, and that is called the Pulse algorithm. We combined several ideas from previous versions and created a tailor-made version of the algorithm that finds the routes with our specific characteristics. Having seen how the first and second stage models work, let's see how the feedback helps us create a good approximation of the routing cost as a function of the depot and fleet size configuration for the first stage model. Intuitively, for a specific depot configuration, this is really important, the routing costs depend on the fleet size in this way. For small values of the fleet size, the routing costs are high, but very sensitive to small changes on the fleet size. Whereas for large values of the fleet size, we have relatively low routing costs and the change on the fleet size has a low impact on the routing cost. Using the traditional vendor cuts with each evaluation of the second stage, we can locally approximate this function. So, if we query several times the second stage subproblems for the same depot configuration, we obtain a good approximation of these functions. One problem is that the routing costs depend not only on the fleet size but also on the depot configuration. So, when the depot configuration changes, the approximation that we had is no longer valid. In reality, this is how the functions that we are trying to approximate look like. For each possible depot configuration, there is one of these functions, and for each depot configuration, we need to create its own approximation. This way of providing feedback between the two stages, to the best of our knowledge, is one contribution of our work, and we will call them the MaD cuts. We have now discussed how the optimization process of our methodology works. Now, we will come back to explain how the scenario generation phase is structured. This scenario generation phase is composed by three main stages. First, a careful data analysis is made in order to understand the behavior of the demand. In this stage, valuable insight of how the customers order and how much they order is obtained. Second, with all the insights gained from this data analysis, a simulation model of the demand is made in order to generate a large amount of observations. In this simulation, we need to keep in mind that the probability distribution of the aggregated demand and the spatial distribution of the generated scenarios need to match the actual historical data. And third, a scenario selection mathematical model chooses a certain number of scenarios that match a specific risk profile. This methodology allows us to find high-quality solutions. Nevertheless, we wanted to improve computational times. In order to make our methodology computationally trackable and more efficient, we developed several acceleration strategies that tackle different obstacles faced by the plain vanilla version of our methodology. We would like to focus on the two most relevant ones. First, a route generator activation paradigm guides our main optimization procedure. In each iteration of the main procedure, the route generators are called within each of the scenarios several times. In sum, this would take the greatest portion of the total execution time. We found that it is not necessary to create new routes in every iteration of the main procedure, so we only generate routes when it is actually worth it. This acceleration strategy establishes two moments in which routes are generated. First, in a preprocessing phase, in which the set of routes of each scenario is initially filled with high-quality routes. And then, when the current best solution changes. Another relevant acceleration strategy is this root recycler. Since in every iteration of our methodology we need to solve multiple times a multi-depot VRP for different demand scenarios, we propose an acceleration strategy that maps the set of roots generated from one second stage problem data into another, keeping in mind the costs through a savings function and the routing constraints. This is the big picture of our solution strategy. MaD Condor contributions can be found all over. But our main contribution is to articulate all these elements into one complete solution scheme. After discussing our solution strategy, we will present our results. But before doing so, we need to keep in mind that depending on what part of the demand distribution the scenarios come from, one can focus on different risk profiles. If we focus on the whole distribution, we would probably be matching a risk-neutral profile since we are preparing for the most common scenarios. But if we focus on the right tail of the distribution, we are probably matching a more conservative risk profile since we are preparing for the worst-case scenarios. So, in order to provide a more complete solution and more alternatives to the decision maker, we use the flexibility of our methodology and provide, first, a solution that considers the whole distribution, henceforth the expected value solution, and also a solution that considers only the right tail of the demand distribution, henceforth the conservative solution. With this in mind, we use our methodology to obtain a depot and fleet size optimal configuration for both alternatives. The depot fleet size configuration obtained with the expected value scenarios opens 3 depots and allocates 15 vehicles, whereas the conservative solution 5 depots and 21 vehicles. In both solutions, we can see depots located on the outskirts of the main demand concentrations, this aiming to reduce the transportation costs without incurring high depot maintaining costs within the urban areas. Additionally, as expected, the depot and vehicle maintenance costs of the expected value solution are almost 37% cheaper than in the conservative case. This implies that the daily cost of being prepared for the worst-case scenarios is of $566. This does not necessarily mean that the expected value solution is better. Before jumping into conclusions, we must first consider the daily routing costs of each of the solutions. The only fair way of comparing the daily routing performance of each of the solutions is to test them with real demand data. For this task, we use the datasets for 2018 and 2019. For comparing the performance of each of the solutions, we first consider the daily routing costs. Since we are talking about uncertain demand, these are random variables, and in order to compare them, we must take several measures into account. As we can see, the expected routing costs of the conservative solution are around $500 cheaper than for the expected value solution. When considering the standard deviation, we confirm that the risk taken by the conservative solution is lower than the one taken by the expected value solution. And finally, we can see that for the worst scenario with the expected value solution, we have a routing cost that is around $2,600 greater than with the conservative solution. With this characterization, we can now compare the expectation of the total daily operation costs. This, taking into account the deterministic and the stochastic components of the total cost before mentioned. In order to compare this expectation, we performed a t-test and we found that there is enough statistical evidence that shows that the expected value and the total daily operation costs of the conservative solution are greater than those of the expected value solution. However, there are other metrics that the decision maker needs to consider when deciding its solution. First, the average vehicle utilization of the expected value solution is 92.2%, this meaning, on one hand, that the resources are used in a more efficient way, but also that there is no slack for responding to unexpected high-demand scenarios. Second, the decision maker can consider that the daily expected CO2 emissions for the conservative solution are 0.8 tons per day less than with the expected value solution. And third, the expected value solution does not fulfill the total demand in 54 of the 730 days tested, whereas the conservative solution is able to serve all the clients in all the tested days. Finally, we would like to talk about the computational times in which we found each of the solutions and show the impact of our acceleration strategies. Before the automation of the decision of the number of depots and implementing most of the acceleration strategies in order to obtain the optimal depot and fleet size configuration for each of the alternatives, we needed to run our methodology many times with different number of depots to place. In these bar charts, we report the running times broken down by phases. Here, we can highlight that the automated model is approximately 2.7 times faster than the one we proposed before. The phase with the greatest speedup is the root generators phase, which is up to 10 times faster in both solutions. The total time for the user is about 6 hours for the conservative case and 1.5 hours for the expected value. The acceleration strategies have a huge impact on the computational times for solving the writing problem. Let's focus on the conservative execution times. With acceleration strategies, we were able to solve the 730 instances in 1/5 of the total time of the plain vanilla approach. Also, we can now solve 75% of the instances in less than 3 minutes each. Finally, we will show the main functionalities of our AIMMS decision support tool. We have built a web user interface for our AIMMS application that is oriented towards the daily operation of our company. This is our homepage, and at the right, we can find the menu that contains our 3 main pages: Input Data, Depot Locations, and Enter Your Own Demand. The Input Data page allows the user to change some of the main parameters of the problem. In the location summary, a location can be selected to set if it's a potential depot or not, and modify its maintaining cost. The Vehicle Parameters section will allow changes in the cost of vehicles, their capacity, their speed, and fuel efficiency for environmental metrics. Also, the sliders at the right allow us to change both time windows, the one for the vehicles and the one for the clients. In the Depot Location submenu, we can explore the first stage solutions obtained for the expected value scenarios and the conservative scenarios. At the bottom, there is a breakdown of the total daily operation costs, and we can see what percentage of the total cost each of the components make up. There is also a global summary, when we can see the costs, average demand, and average number of clients of the selected scenarios. If we change the selected solution, these values also change. Also, if we select each of the depots, in the depot summary we can find its zip code, location name, and the number of vehicles located at this specific depot. In the Enter Your Own Demand page, we can upload a file that contains the demand of each of the clients for any number of days. Then, we can select to route the vehicles by recycling routes from a collection of path-generated routes, or we can route the vehicles through the column generation approach we discussed earlier. Once we select the solution method, the screen will show a busy message on the top left corner. Then, when all of the uploaded instances are solved, the results will appear on screen. A summary of the solution will appear for the scenarios uploaded as input. On a selected scenario or day, the routing costs, service level, vehicle utilization, and other useful metrics are displayed. If a depot is selected on the map, its zip code, name, fleet size, and average trip duration in hours will appear on the summary on the left. Also, on the right, every delivery trip is displayed. This schedule shows the overall time of the vehicle as well as its departure time and arrival time to the depot. Finally, the user can download the report of the schedule for each vehicle as a timetable. It contains a detail of the number of units to deliver, the departure time, the expected time for delivery, and the maximum arrival time to each location, so the route is still feasible in the time windows. This provides a good tool to drivers and managers to adjust plans on the go. To conclude, in terms of the methodology, we provided several specific contributions that tackle specific aspects of the problem, but the articulation of all these elements into one complete solution scheme, we consider it's our main contribution. Second, we use the flexibility of our solution scheme for providing different alternatives to the decision maker. Which solution to use is up to the decision maker and its risk profile, but we provide the pros and cons of each of the solutions. And last but not least, we developed a handy and versatile decision support tool oriented towards the daily operation of the company and that provides ways of routing the vehicles for any demand scenario. In this way, since the demand is revealed at 6 p.m. the day before, in most days by 6:03 and by 6:45 at the latest, the vehicles can be loaded and with its respective schedule ready to depart the next day. Thank you.